Hello everybody and welcome back to episode 5 of my video series in which we program an entire video game from scratch from beginning to end. I got a couple of comments on my videos previously and I wanted to go ahead and address those things. The first thing is, let me find it over here. Basically someone made a comment asking if I could address the concept of integer overflow, which is something that I never did before. So I will go ahead and do that. And basically, what I'm going to do is have our project open over here, and I'm just going to kind of push that to the side for right now. Start at the very beginning of our main function. And I do remember last time I went into a pretty good amount of detail as to what the int or integer data type was. So if we declared an integer like this, and let's say we made it 0. What if we were to do this? What if we were to try to assign, we know from last time that the most that an integer can hold is 32 bits, right? So what if we, and before it actually needs to be an unsigned integer, because remember, we're going to try to put an unsigned integer in here, which is 32 bits. That's like 4.3 billion, right? So, well, what if I try to add one more to it? Let's run the cursor, and let's look at my. There, I have overflow, and let's assign to it. I'll step over by pressing F10. And it looks like the value of overflow didn't change. That's weird, huh? Let me go back here. Let me take away the +1. Oh, yeah. And now that I've already compiled, the compiler now warns me that I have a potential arithmetic overflow. Run the cursor. Here's my overflow variable. There, I take one step and I've now assigned the overflow variable a value of 4.3 billion. Which that number is the same thing as 8 Fs in hexadecimal, which we'll still get to the hexadecimal part later. One thing at a time. Alright, so now we're back to where if I assign it one more than that, remember this is the maximum amount that an unsigned integer can hold, because it's all 32 bits have all been flipped on. And if I add one more to it, it looks like it's staying at 0. And my guess is that's because it's rolling over. It's like the odometer on your car when it hits 999,000 miles or whatever, it flips back over to 0. Let's do +2 and see what happens. See, this time, so what I did, now our overflow variable has a value of 1 assigned to it. And if you look and wonder how the heck that happened, it's because we assigned as much as we could to it. You add one more to it, it rolls back over to 0, and then you add one more to that, and now you have a value of 1. So you've effectively rolled over. And you could do this with any data type. Here's another example, a much smaller example. Unsigned char equals 255. So a char, or is short for character, but it is 1 byte. It's like the smallest data type that you can work with, generally speaking, is 8 bits, which is a byte. And we need to name it, don't we? So now if I add one more to it, it should roll over to 0. And let's see. See, right now it's 255. I'll make one more step through the code, and now it's back to 0. See right there, A now has a value of 0. Okay. And by the way, this means this is just shorthand for A equals A plus 1. It's just a way of incrementing the variable by however much you want to increment it by. If I take the unsigned keyword away and I just have a char, now a signed char character or char data type cannot hold a value of 255. So this is kind of nonsense right here. These are some of the little subtle bugs in C that the compiler doesn't always warn you about. Because remember we have all warnings enabled, right? And the compiler still probably won't warn us about this. So you can see now that A, that I've assigned it a value of 255, has now rolled over to a -1. And I can have negative numbers because I took away the unsigned keyword. So now the most significant bit is reserved as the signed bit to whether the number is positive or negative. So I could do 1. So I should be able to do a -127 should be the smallest number that a signed char should hold. So what if I did the least it could, the smallest number it could hold, and then subtracted one more from that? I predict what will happen is I'll roll back over the opposite way and have a positive 127 as a result. So if I run there and then step 1, or okay, negative 128. Am I wrong? Is it -128 instead of 127? Let's try it again. There. This time it rolled over to a positive 127. So for some reason I thought -127 was the smallest that would fit into a signed char variable, but apparently it's 128. But anyway, that does get my point across. We rolled back over the opposite way, and it turned into a positive 127. So that's essentially, rollover, and the compiler won't warn you about this generally, which is weird. Initializing truncation from int to char, that's fine. Variable initialized but not referenced. So yeah, anyway, it's just something that you have to be mindful of, and we'll probably experience, we'll definitely experience more of this later when we have to convert from one data type to another, and it's very common for a function, for example, if we call a function that returns an int, but we want to store the result of that function into maybe a short variable, so we have to basically truncate it, and the compiler will definitely want to warn us about that, that we're basically trying to stuff an integer return value into a smaller data type, and very strange things can happen when you do that. So that is one thing that the compiler will warn you about. Alright, let's take all that away. Now, the same person also asked another question. And this question was, they say, I always have the warning when main must be __ std call. They made a quick research for this in Google, but they didn't find an answer about this warning. And oddly enough, that's weird because I've done every step of this right here on video, and I don't have that warning. So he must be doing something different than what I'm doing. Because notice I don't have that warning, and the warning is I'll write here. I'll copy paste it. WinMain must be std call. So this is a pretty important discussion. This discussion brings us to the idea of calling conventions. And I think the easiest way to first start to explain this is that the reason why, I'll tell you right off the bat, the reason why the person who commented on my video has this warning and I don't, is because the person who made this comment is compiling for x86, whereas I was compiling for x64. If I compile for x86 and then do rebuild solution, now I have the warning too. WinMain must be std call. So here's how you fix this. We could do std call, just like that. It's a, I guess, what do you call this? A decoration. You're basically just, it's where you put this little keyword in here to tell the compiler that this function is going to be using the standard call or std call calling convention. And let's build, rebuild, and the warning went away. So to answer your question as easily as possible, yeah, it does need to be std call when you're compiling for x86. All of the Windows API functions, as far as I know, they're all std call. And std call is a calling convention. Basically, calling conventions are it's the protocol that one function uses to call another function, and then that called function uses to then return to the previous function. There's a protocol on how those functions have to talk to each other. And in fact, if I were to just right click and run to cursor here and go to the disassembly right here, and then let me move the disassembly to somewhere else. I'll put it like right here. There we go. Now this is the machine code that our compiler is generating based on the code that we wrote. But if you read it, you'll notice that there's a lot of stuff that's going on here before it ever executes any of our code. Like, for example, here's where the WinMain function starts. All this code, this automatically generated code is running, and it hasn't run any of our own code that we wrote yet. So the simplified way to explain this is this is the function prologue. Every function has automatically generated code at the beginning and the end of it. The compiler automatically generates some code at the beginning of the function and at the end of the function. And this is not code that you as the developer write. This is code that the compiler automatically generates. And we call these things the prologue and the epilogue, and they are at the beginning and the end of every function. It'll be different depending on which calling convention you use. In the std call calling convention, I think it's I better get this right before I say it on recording. Okay, let's see. Yeah. Okay, fine. Because I always get it confused between caller and callee. So in the std calling convention, stack cleanup is performed by the called function. In contrast, there's another calling convention called cdecl, and that's the opposite, where if you use the cdecl calling convention, it basically says that the caller is going to clean up the stack. And when I say the stack, the reason why that's important right now is all the arguments that you pass into a function. A lot of those arguments are passed over in this area of memory called the stack, and these functions need to know ahead of time who is going to clean up the stack. When one function calls another function, he basically has to push all of the parameters that he's going to send to that function onto the stack. That other function that just got called is going to run, but then it's important for that other function that just got called, he needs to basically restore the stack to its previous how it used to be before he got called, before he returns, so that then the caller can then resume execution with his stack the way that it was before that other function started running. Anyway, all Windows API functions use the standard calling convention, and remember, this is basically just in the context of x86. This doesn't necessarily apply to x64, which is why I wasn't getting that warning in the first place. But this is still important history that we really need to know. So one of the most straightforward examples of why any of this is relevant is the printf function, for example. So let me just stop this. Now you might remember our old friend printf. In that, with printf you can supply an indeterminate number of arguments to it, right? And that's not the same as with a function like WinMain or any other Windows function like MessageBox-A. Notice that in MessageBox-A, if I hover over it, you can see that it also uses a standard calling convention, as all Windows API functions do. And you can also notice that it's not variadic. Variadic is another word that just means it accepts a variable number of input parameters, like printf does. Printf, on the other hand, you can see that it is cdecl. This uses the cdecl calling convention. That means that you can give it an indeterminate number of inputs. That is the reason why you might want to use one calling convention or the other, is if you want to make a variadic function. And there will come a time when we will want to make a variadic function. This message box is a great example. I don't like the way that I can't give this message box an error code. I would love it if I could treat this message box just like I do 0x% LX. I would love it if I could treat the message box function like a printf and just start pounding in variable arguments here, like get last error. You know what I'm talking about? So that way I can put the last error right into the message box. Okay, but I can't do it because it uses stdcall. So because the stack is cleaned by the called function, the std calling convention creates smaller executables than cdecl. I'm reading some notes over here, in which the code for stack cleanup must be generated for each function call. On the other hand, functions with the variable number of arguments, like printf, must use cdecl because only the caller knows the number of arguments in each function call. Therefore, only the caller can perform the stack cleanup. Okay, now we're done with that. Clear as mud. So there's also a pound define somewhere in the windows.h header file. You'll see this a lot too. This is the same thing. If you hover over it, you can see that WinAPI is just directly pound defined as std call. So you'll see that a lot. I think you'll also see this one a lot too. It's the exact same thing. So it doesn't matter if you use the alias or if you use std call directly. Either way works fine. Now back to x64. In x64, everything is different. Basically, in x64, we use another calling convention called fast call. Which looks like this. And it's used as much as possible. It's used everywhere. So that's why whenever you compile this code in x64, you don't get a warning about WinMain needing to be std calling convention. However, if you do it in x64, what in the world? Oh, I messed up my message box function. Yeah, you don't talk and mess with message boxes at the same time. Anyway, but if you do specify std call there, it's still going to work fine if you do it. That reminds me, there's a couple things in the properties of my project that I wanted to change, and those are, if you go to, let's see. So in the advanced section under C++, it actually allows you to specify the default calling convention that you want to use, and it's on cdecl by default, and I would probably just leave it like that. There's one other thing. I think it's in. Let me check again. I don't remember if it's in. I don't know why I can't find it. Maybe it's in here. No, it isn't. I'm just missing it. There it is, right here. Jeez. Okay, support just my code debugging. This was on. This is the just my code. Now this is a new thing, and I'm gonna turn it off, but I'm gonna show you what it does first. I think this is a new feature in Visual Studio 2019, where, let me do just what I did earlier. Run to cursor, and here we go. It actually generates additional code, and it is basically just for debugging purposes. It's supposed to make your life easier as a debugger by basically skipping over, having the debugger skip over any code that isn't the code that you wrote, that isn't your code. However, I am not familiar with it, and I've never used it before, and sometimes I want to show you code that isn't necessarily ours. It may be code that's running in the Universal C runtime or something like that. So just in order to not confuse myself, I'm gonna turn that off. But I wanted you to see what it does first. It looks like it's before every function call. It's probably generating this extra code. See, I don't see any more yet. Anyway, let me stop this. I'm gonna go turn all this off. Okay, so now we've discussed integer overflow, and we've discussed calling conventions. Oh, and by the way, the fast calling convention, which is what we use in x64, it's called fast call, and it is used everywhere on x64. And the reason why they call it fast call is because it attempts to stick the input parameters of every time you call a function. It tries to stick the input parameters of that into CPU registers, and CPU registers are generally faster than um, data that's stored on the stack. Um, by default, or on x64, the parameters are passed in basically C, D, R8, and R9, I believe it is. And what I mean by that, let's do this one more time. Run the cursor. Yeah, so from right to left, we are basically taking these are our input parameters, and these are CPU registers. When I say you know C, I mean RCX. When I say D, I mean RDX. So RCX, RDX, R8, and R9 is where you're going to see input parameters being passed. And the only reason that wouldn't happen is if maybe they didn't fit in a register. Sometimes sometimes you have more than four input parameters, so you may only be able to fit the first four input parameters into the CPU registers, but then every parameter after that, the fifth and the sixth parameter, those you might have to store on the stack. Okay. I think that's it. Let's see. One other thing I wanted to do. Oh yeah, this reminds me. This our game window handle. I think it's actually supposed to be an H-wind. Um, Probably doesn't matter, but there we go. And the reason I am thinking that is because we created it in the create main game window function, right? So if I go down here, the create window ex function returns an hwind, not a handle. So our g game window variable should be an hwind and not a handle. A handle to a window. It works fine no matter which way you do it, but you know. All right. So let's move on. We wanted to do, here's our game loop, and we want to get to, eventually we want to get to the graphics part of this, right? We actually want to draw something on our silly little window. Speaking of which, I'm going to go over here. We're going to change this eventually, but I'm going to go to create main game window. I'm going to make our window bigger, something like 640 by 480. Okay, yeah, now our window is bigger by default. We're going to be changing that again later, but for now that's fine. Okay, so let's go ahead and go back to our main game loop here, and let's go ahead and turn render frame graphics into a reality. By that I mean I'm going to go over here to main.h, and I'm going to declare it as a real function. And this function is not going to return anything. It's not going to accept anything as an input parameter. And there's two reasons for that. Basically, one is just that it's not going to return anything because I basically expect for this never to fail. Like, I'm never going to accept in my program for there to be a situation where graphics just don't get rendered. Like, that's just not something that I'm ever going to allow that to be possible in this program, okay? It's never going to fail. So it doesn't need to return anything. Secondly, it's not going to accept any input parameters because, well, two reasons. I think I don't think it needs any yet. If it does need any, then I'll give it some, but I would rather not. And the reason why is because parameter passing slows us down. And depending on how you do it, it can really slow you down. So since this is our main game loop, I need this to run as fast and as efficiently as possible. And yeah, so I'm going to try to avoid parameter passing as much as I can in terms of this render frame graphics function. So I'll just start with no parameters for now. I'm going to go down here and define it. All right. So the next thing we need is we need basically a drawing surface to draw on. And this drawing surface is our canvas, basically. This is where we're going to draw all of our graphics. It's going to be stored in memory, and then every frame, what we're going to do is we're going to do all of our drawing on this thing in memory, and then we're going to take our finished canvas and paste it all in one shot onto our window so that the user can see it. And the reason for doing this is because if in Windows, if you try to draw on the window, if you try to draw directly to this window, say if I drew my background onto the window and then I drew each little sprite onto the window, what ends up happening is you end up with a lot of flickering. You end up with a lot of flickering is basically your biggest problem. Flickering and VSync problems, things of this nature, and it looks really terrible when you do it that way. So what we need to do is basically we need to write all of our changes to our in-memory buffer, and then draw just once per frame onto our game window. That way it'll look a lot smoother and it won't be flickering. So let's go ahead and create our in-memory, whatever you call it. Let's go ahead and create that. So the simplest form of this would just be a pointer. Basically, a pointer is it's going to be the size. It's a memory address. Basically, a pointer is a memory address, and the size of it is going to be based on the architecture that you are designing for. If I compiled this in x86, then my pointer, my memory address, would be 32 bits. If I compile this for x64, then my pointer will be 42 bits. However, having just a memory address of where my drawing canvas in memory is not enough, because I also need to know things like the dimensions of this drawing canvas. Like, what is the height and the width going to be? Is it 640 pixels wide by 480 pixels tall? We also need to know some other things like, what the bit depth of it is. Is it going to be 32 bits per pixel? All this kind of stuff. So because we need multiple pieces of data inside of one thing, this is our perfect opportunity to create our own data structure. And so that is exactly what I'm going to do. I'm going to call this, I'm going to create our own data structure, and I'm going to call it something. I'm going to call it a game bitmap. Now, inside of a data structure, you can have all sorts of things. This is the cool thing about a data structure, is that you can have multiple other types of data inside a data structure. So, for example, I could have my memory in there, and then I could also have a int height, int width, int color depth, I guess maybe, or we'll do bits per pixel, like that. So what I could do, oh, and let me go ahead and add a type def to this. What the type def allows me to do, the type def isn't actually strictly necessary, but it's a convenience. What it allows me to do, it's despite the name type def, it's not exactly creating a new type, a new data type. It's not that exactly. What it's creating an alias basically. So what I can do is I can create like I can now create my new game bitmap because I've defined it over here as a data type. So what I want to call it, canvas maybe, or drawing surface maybe. There. And I've initialized it to all zeros. Sorry, my eye is itchy. And you can see that now I can do drawing surface dot height equals 480. I can do drawing surface dot width equals 640, and these sorts of things. And that's pretty good, right? However, I happen to know of something that might make our lives easier beforehand. And there is another data structure. You can actually have data structures nested inside of your data structure, nested inside of other data structures. So what I'm going to do is, I happen to already know of one that is defined in Windows.h, and it's called a Bitmap Info. And there. Inside the Bitmap Info, it already contains members for height and width and bits per pixel and all this kind of stuff. So I don't need my own. I don't need to define my own anymore. I can just have it like that. So now I have basically inside of my game bitmap data structure, I have a bitmap info, which this is defined in Windows.h and contains a bunch of other, it's a nested data structure. And then I also have my pointer, which points to my memory. Okay, so I think that's all we need for that. So back over here, this is not relevant anymore. I've declared my game bitmap, and I can tell you right now that's going to need to be a global, isn't it? Game bitmap. G drawing surface. Okay. Now let me go find a good place to, I guess somewhere after I've created my main game window. At that point, I suppose I will initialize the new drawing surface that I just created, right? So drawing surface dot bitmap info, my header dot PI size equal size of drawing surface dot PI header. And this is similar to, remember we've done this once before in our create main game window function. We had to do the same thing where when you have a data structure, a lot of times the first thing that you need to do with it is fill out the size member, which is literally just the size of itself, the size of the data structure itself. And so you basically do that just so that when you call a function, it knows how to handle, like it knows how big this data structure is going to be. Anyway. All right, let's keep going. Drawing surface dot bitmap info dot BMI header BI width. BI width is going to be, how big is it going to be? This brings us to another important discussion that we've never had, is what we want the actual resolution of our game to be. Now, if I were to if I were to look up, say, NES resolution, the standard display resolution of the Nintendo Entertainment System is 256 by 240. 256 by 240. So we could just start we could just start like that and say we want our game to also to mimic what the NES used to do. So it was 256 by 240. And we could just go with that. Oh wait, this needs to be height. Okay, width and height is 256 by 240. There's a problem with that though. And the problem with that is the aspect ratio is not what we typically use today. And what I mean by that is 256 divided by 240 is 1.0. It's like back in the day, a long time ago, 1980s, 1990s, and early 2000s, everyone had television sets, and these television sets were always at a resolution of 4:3. Somewhere along the lines, that has changed. In the late 2000s and early 2010s, there was a big shift to where everyone now has TV sizes that are 16 by 9. Almost everybody uses televisions and computer monitors that have an aspect ratio of 16 to 9. I mean 16 to 9. So 16 units across and 9 units high. And that means, so for example, if I looked up 1920 by 1080, or sorry, 1920 divided by 1080, that is a 16 by 9 aspect ratio. So if I used a resolution like 256 by 240, obviously I'm going to scale that up because 256 by 240 is very tiny and you'd barely be able to see it. So I have like this, 2,560 pixel wide display. It would be, the size of a postage stamp on my monitor. So I'm obviously going to have to scale that up, but the aspect ratio will stay the same no matter how big I scale it up, right? The problem is that I know that it will not fit inside of it won't be the same aspect ratio as my 16 by 9 monitor. So what I'm going to end up with are some black bars, probably black bars along the sides of the monitor. And maybe I can live with that. I don't know. So let's actually look up some. Let's see. 256 by 240. Oh, here's an interesting fact: is that the Super Nintendo actually has a resolution of 256 by 224. So counterintuitively, the Super Nintendo actually does have a smaller resolution than the older NES. The SNES makes up for it in having way more colors. Basically, is the whole thing that makes the SNES graphics look way better. So I don't know. There's a lot of issues with this. It's the wrong aspect ratio, even though it does give us like that sort of nostalgic feeling of having NES resolution. That still may not be right for us. And here's what I'm thinking. If I look up, for example, there's a game that I played recently, and it's really good. It's called Shovel Knight. And let's see, yeah, find some. No thanks. basically it looks like this. There we go. And you play it with a, I played it with an Xbox 360 controller on my PC, and it's a really awesome game, and you should play it if you haven't played it. However, so you can tell that they were going for a retro look in their game, just like I'm going for in my game. But they're using a more I can already tell you that the aspect ratio of this is not the same as an NES. It looks wider, doesn't it? Looks much wider. So let's go look up what is the actual resolution of Shovel Knight resolution. Okay, they used 400 by 240. Each Shovel Knight pixel is really 4.5 by 4, 5 pixels at 1080p, giving a virtual resolution of 400 by 240. NES outputs 256 by 240, giving us the same vertical resolution. Our background tiles, like most NES games, are 16 by 16. I like that idea. I want to have 16 by 16 tiles too. We have the same number of vertical tiles as an NES game. So we might actually end up copying, I think we might copy what Shovel Knight did, because Shovel Knight looked really good. It definitely had the nostalgic feel of an NES game, but it also adapted to the fact that we don't use 4x3 displays anymore. Everybody's using a 16 by 9 display. Everyone is using a widescreen display basically. So we may actually just follow their lead and do a 400 by 240. Also, I don't like just plugging in numbers like this. I think it's better if we define them. That way, if I have to change the resolution of the game later on, I don't have to go and look for multiple places throughout my code where I may have just hard-coded 240. I can actually do a let's see, game resolution, game res width is going to be 400. Game res height is going to be 256. 256. Okay, 400 by 256. No, that's not right. 400 by 240. Now the aspect ratio of this is still not going to be 16 by 9. Let's do. It's still not 16 by 9. I wonder if we could do something. I wonder if we could do something smarter. Let's look 16 by 9 resolutions. Okay, common list of true 16 by 9 resolutions. Okay, I like this. I also like that it tells me which ones are divisible by 8, because being divisible by 8 is going to be important to us, probably, especially if we're using 16 by 16 tiles. You know, basically when you're programming, having things being cleanly divisible, the gods will smile upon you if you have everything be cleanly divisible by either 2 or 8 or 32 or 64, things of this nature. So 256 by 144, it's a bit small. 384 by 216 is a bit small. Okay, 512 by 288 is a 16 by 9 resolution. It's small enough that it may still look, it will have that sort of chunky NES or maybe SNES look to it, but it's also 16 by 9, so I'm basically thinking one of these two, either 384 by 216 or 512 by 288. I'm afraid that 512 by 288 might not look pixelated enough, so let me just start with 384 by 216. 384 by 216. I don't know. We may change it again later. But at least now this is a proper, at least we know that this is a 16 by 9 resolution, which means it will fit a 19 by 20 by 1080 monitor. It will fit a 2560 by 1440 monitor. It will fit a 4K monitor because those are all 16 by 9. Okay, let's keep going with our little pound defines here. Game bits per pixel is going to be I can already tell you right now that we're going to be using 32 bits per pixel, and this is one of these situations where we are taking advantage of the modern conveniences that they didn't have back then when in the Nintendo or Super Nintendo era. Now, a Nintendo, an NES cartridge was 40 kilobytes. They had to fit an entire game in 40 kilobytes, and then they had to run it on like an 8 megahertz processor. I don't remember what the speed of the NES was, but it was something like that. It was just a few megahertz, very slow, very very small, and they had to employ all sorts of crazy tricks to try to make their game fit into a 40 kilobyte cartridge and run as efficiently as possible. We, on the other hand, are on a 3 gigahertz machine with 32 gigabytes of memory, and we can basically take a lot of breathing room because we're not under these constraints of running on ridiculously slow and small hardware. So I'm going to use 32 bits per pixel because that means we don't have to worry about compression. We don't have to worry about canvases. If you later on when we go to loading bitmaps into our game, you're going to see how much easier it is to work with 32 bits per pixel bitmaps versus, like, say for example 24 bits per pixel bitmaps. And the reason why is because 24 bits per pixel bitmaps, even though they're a little bit smaller, you also have to figure out all these like canvases and like pixel compression stuff that you have to work with, and it basically just is annoying. When you can use 32 bits per pixel bitmaps, you basically can just work in pure RGB. The downside is that your bitmaps are going to be like 1 or 2 megabytes if they're big. They can be huge. But you basically have room to stretch your legs out and work in pure RGB. It's also faster. So counterintuitively, you would think that working with a 24 bits per pixel graphic would be faster because it's fewer bits, right, for the CPU to have to work with. It's fewer than 32, so must be faster, right? Turns out it's actually slower than working with 32 bits per pixel, and that comes down to basically any amount of data that is a base 2 number, so like 2, 8, 16, 32, 64, 128, 256. So it's like a factor of 2, right? Or it's a base 2 is what I'm trying to say. Is going to end up being faster because of the amount of data, like the size of the data pipelines that your CPU is designed to work with at once. Is basically, it's going to be like 32 or 64 or 128. We'll see another example of this. We might see an example of this here in a second when we try to compile this data structure right here, and it gives us a warning about it being of kind of a funky size. It's not cleanly divisible by 8 or 32 or whatever. Anyway, let's go back over here. What am I missing? we need to make one more define here, and we're going to say game I don't know if it should be I don't know if canvas is the right word. Game drawing area memory size. Okay, and it's going to be basically our width, which is game res width, times our height, times times our bits per pixel divided by 8. So our 32 divided by 8 is 4. So it's we have 32 bits per pixel, which equals 4 bytes per pixel, times our height times our width. That's going to equal, that's how much memory we need for an entire frame of our game. Each frame is gonna occupy that much memory. Okay, so now back over here, we can do game res width, game res height. We're coming up on an hour too. Let's see here. Let's keep going. Let's see, G drawing surface dot bitmap info dot be my header. We're basically filling out our little bitmap info structure bit count, and this will be useful if we ever have to use any sort of like Windows API bitmap processing function that needs a bitmap info data structure. We'll have one ready for it. So we're basically sort of making ourselves compatible with the Windows API so that Windows API functions will be able to operate on our customized drawing surface. Oh, okay. BI bit count is what? Bits game BPP. G drawing surface info. Get my header. The BI compression equals BI RGB, which basically means no compression. We don't have to see it's defined as 0. We don't have to worry about compression because we're using 32 bits per pixel. It's just one less thing to worry about. My header dot BI planes equals 1. Alright, I think that's it. Okay. The last thing we need to do is we need to actually allocate memory for this thing, which is kind of the most interesting part of this. So we'll do G drawing surface dot memory equals, we have to allocate memory. So when you allocate memory in Windows, you're going to be using either virtual alloc or heap alloc. I would use virtual alloc anytime I am allocating a large chunk of memory that's maybe like 64 kilobytes or larger. Virtual alloc tends to allocate memory in large chunks. So if you use virtual alloc to make very small memory allocations, you could end up wasting a lot of memory. So if you use if you just need 2 or 3 bytes of memory, I would use heap alloc instead of virtual alloc. But since this is a big one-time memory allocation, virtual alloc will be fine to use. And I think it's all right. Address, by supplying a address of null, that means we're just going to allow the Windows memory manager to give us a memory address. Like it will create the memory wherever there's room for it. The size of it is going to be that thing that we defined earlier. which is game drawing area memory size. That's how much memory we need. The type of allocation is going to be, we're going to reserve, and we're going to commit the memory. And then the protection of the memory, we are going to need to read from it and write to it. So I think read write, not read only, read write. I think that's right. Okay. I think that is correct. Now, we want to know, we would like to know if allocating this memory fails, because it could fail if the machine is really out of memory. It's just a good practice to always check for that condition. So this function, you can look up virtual alloc on MSDN or docs.microsoft.com. But in the interest of time, if the function fails, it's going to return null, which means we won't have a memory address. It won't assign a memory address to our memory attribute or field over here. So what I'm going to do is I'm going to make it like this. I'm going to say if, and this is a way that you can do variable assignment and comparison all at once. We're basically saying if that equals, if the result of all of that stuff equals null, then I want you to tell us that we failed and exit the application. Just like that. So it's basically saying, I want you to call virtual alloc and assign the result of it to gdrawingsurface.memory. But if the result of that happens to be null, if you assigned null to it, then we know that it failed, and if it failed, I can't continue on with the game. I need to go ahead and quit. So I'm going to go ahead and copy one of these message boxes that we did earlier. And I'm going to type failed to allocate memory for drawing surface, and then it gives me an error and returns 0, or go to exit. Doesn't really matter. So you don't have to do it like that. You could also do it like this in 2 different lines if you wanted to. Equals virtual alloc, put a little semicolon at the end of that statement, and then I could do if gdrawingsurface.memory equals null, then we know that it failed. Okay, so let's see, I think we're probably out of time. Okay, everything still works fine. We got an interesting error here. Game bitmap. 4 bytes of padding added after data member bitmap info. So 2 things to note. That warning is generally considered to be not important, but I still want to explain it anyway. I want to explain why that error occurs. We wouldn't ever see that error if we didn't have all errors turned on. But yeah, there is some padding here. And if I add 4 bytes, and that's how big an int is, right? 32 bits, 4 bytes. If I added my own 4 bytes here and compile it again, the warning goes away. But there needs to be 4 bytes there for optimal CPU processing efficiency, and I will explain why to you. in the next episode because it looks like we're out of time. So next time we're going to, we got our drawing surface prepped and ready. And next time we're going to just go and slap it onto our window, and we'll finally have a drawing area that we can draw to. So if you have any questions or comments, feel free to leave those comments on the video, and I'll address them in an upcoming video. And like and subscribe and follow me on Twitter and all these things, and I will see you next time. All right, take care. Bye.